Okay, this is the last example I want to give for chapter 6, example 6.6. Okay, the problem is like this. That's a wind tunnel. It's a it's a tube. Basically, it's a circular wind tunnel. Okay, with a diameter of d. Okay, in the wind tunnel, there's a object. Let's say an airfoil or whatever shape of the object in there. The object is attached to the wall with these two supports on top and bottom. So it has been attached to the wall. Okay, so wind tunnel, you blow air to it, right? So for the inlet at section 1, you have a constant velocity, 30 meter per second. And the pressure at the inlet, P1, is 1500 Pascal. Okay, and at outlet 2, the pressure become 1000 Pascal. Okay, P2 is 1000, but the V2 is not a constant. Okay, it's not a constant because obviously because of the blockage of the object, right? You have a object in the middle, so you have zero velocity in the center. So but the velocity getting bigger when you're close to the wall. Okay, you don't know the exactly velocity value because it's non-uniform, but the velocity V2 is linearly distributed on the outlet surface. Okay, at the outlet cross section, it's linear. So I think from the drawing here, it's obviously it's linear, right? In the middle is 0. In the center of the tube is 0. At the wall has the maximum velocity. Okay. So I guess these are the known information. So the question is to calculate the force required to hold this object in place. The force required to hold it. And the force required to hold it actually is, the magnitude is just equivalent to the drag force of this object, right? The direction will be opposite. The force holding it should be towards the left, but the drag force actually to the right. So it's action reaction. So if you ask to calculate the force required to hold this object, basically it means to calculate the drag force. Just change the direction, it will be drag. Okay, let's say Fd is the force required to hold this object in place. So how do we solve it? This seems like a little bit more complicated problem. So couple questions, same questions that you ask yourself, right? Is that steady state or unsteady? Obviously, it's a steady state, still steady state. Every problem we see so far is steady state, okay? It doesn't change with time. Is this uniform or non-uniform? Okay, now you need to look at the separately inlet and outlet. At the inlet, obviously it's still uniform, 30 meter per second, right? But at the outlet, it's a non-uniform velocity at the outlet, okay? So, you need to do integration, at least for the outlet part of momentum. Okay, so let's see if we can draw free body diagram and a momentum diagram. Yeah, we should, right? So notice this, for free body diagram in fluid mechanics, you need to have the object. Most of the time in our object is the control volume. It's not just the airfoil, right? It's the control volume, okay, which is a portion of the wind tunnel, okay? Obviously, your airfoil is inside the control volume. So if you look at this volume, you have to detach the support to the wall, right? Detach the support, you replace by the force required to hold it, Fd. We always specify in the positive x direction for Fd. It will be negative, right? It will be negative, but doesn't matter. We place the Fd, positive x direction, okay? Then you have two pressure forces, P1A1, P2A2, okay? So the force balance, free body diagram is simple. Momentum diagram, okay? You have one inlet, one outlet. Inlet is mass flow rate of the inlet times velocity of the inlet. And at the outlet, okay, we need to use this expression. V outlet rho times V outlet and dA. That's the integration, right? To calculate the outlet momentum. Because V outlet is not constant, you cannot simply calculate the mass flow rate. Okay, so this is the expression. Again, very important, this is the expression. You can separate these two V's. V times V, right, in the integration. You cannot separate them. You cannot say, hey, separate them. One is mass flow rate, the other is velocity. No, they are together. Okay, so based on these diagrams, you should be able to write down the equation. The summation of force in the left-hand side is P1A1 plus FD minus P2A2. The momentum change, outlet momentum minus inlet momentum, right? So summation, integration V2 rho V2 dA2, right? Minus the inlet momentum, which is m dot 1 and V1. Okay, so our unknown FD is in the equation. Okay, it's good. We just need to find out everything else. I think we know P1A1, we know P2A2. We should be able to calculate the mass flow rate at the inlet because we're given the velocity at the inlet. So both mass flow rate 1 and V1 are given. Okay, so the only difficult part is V2. In this integration, I have no idea of V2. Okay, so that's the difficult part of this problem. So we need to focus on calculating this integration. Okay, see the rest of you can substitute all the values, right? And m dot 1 V1 is easy, right? So this integration will become this. Since it's air, the density is constant, is 1 kilogram per cubic meter. So we move 1 outside the integration, so it doesn't matter, right? It's 1. So it's V2 square dA. Again, it's a circular shape, cross section. It's a circular tube, right? So the dA, just like we mentioned previously in chapter 5, dA of a circle is 2 pi r dr. Okay, 2 pi r dr. So the limit of r is from 0 to 0.5, the radius, right? The limit of radius, diameter is 1 meter, right? So the radius is half meter. So the limit for dr is from 0 to radius 0.5. Okay, that makes sense. Okay, so you know what's the goal next, right? Now I have this expression V2 squared 2 pi r dr. So I need to find out a function of V2, an expression for V2 in terms of r. Then we can calculate, we can integrate it out. Okay, so that's our goal. That's the tricky part for this problem. So about V2, I have no information except it's linearly distributed. The function velocity V2 is changed with r, right? Increases with r. So a linear function of V in terms of r should be written by this, right? Should have this form. V2 equal to C1R plus C2. C1, C2 are two coefficients, constants that we don't know. We need to find out. So how do we do that? We have a boundary condition, which we know. The only thing we know is it's the center. When r equal to 0, it's the center. The velocity equal to 0, V2 equal to 0. So we can apply this center condition to this expression. So when r equal to 0, your V2 is 0. So if you substitute these two zeros in that expression, in that equation, it would turn out to be C2 has to be equal to 0. Okay? Two coefficients, we calculate 1. C2 equal to 0. So how about C1? So now we can rewrite it into V2 equal to CR. Since there's only one coefficient, I can get rid of 1, 2, the subscription, right? So CR. Okay, now we need to use an information from conservation of mass. Okay, the flow rate is the same, inlet and outlet. Okay, the volumetric flow rate is the same. Can we calculate the volumetric flow rate? Sure, we can. Based on the inlet velocity and the inlet area, quarter pi d squared times the inlet velocity, that's the Q, that's the flow rate. That flow rate should be the same at the outlet. So we have the expression for V2 at the outlet. So we can integrate this V2 times dA. Okay, that's the volumetric flow rate, right? V2 dA, 2 pi r dr, again, 2 pi r dr times V2. Okay, V2 is CR. So you take integration, it's a non-uniform velocity at the outlet, right? We know how to calculate the flow rate. So velocity times dA, 2 pi dr. The limit is also from 0 to 0.54 dr. So based on that, since the flow rate can be calculated, the value can be calculated from inlet, and based on that expression, you should be able to calculate the C. Okay? If you calculate C as 90, so you know your V2, the expression for your outlet, is 90R. Okay, so notice we need the integration from V2 squared 2 pi r dr. So if we do V2 squared 2 pi r dr, there will be 90 squared R squared 2 pi r dr. Then integration from 0 to 0.5. Okay, but this thing should be easy, right? It's RQ, so 1/4 of R4, right? So with the limit 0 and 0.5, you should be able to calculate this term. Okay? After you calculate this term, rest of them are just calculation, right? You have all the constants, all the values. After you calculate this term, your FD, force required to hold it, can be calculated. 304, negative 304 Newton, which means the force is toward the left, right? You have to hold it, otherwise the flow gonna blow it away, right? And if you're talking about the drag, it will be the same value, 304, but with the positive x direction, okay? Opposite to the force required to hold it, okay? So the drag force will be 304 Newton. The force required to hold it is negative 304 Newton. Okay, this is the last example I want to give. This is a relatively more complicated problem. Okay, it's still steady state, but with non-uniform velocity at the outlet, at least one boundary, right? Okay.